Good afternoon, class. This is the first video for our chapter 12, which we're going to introduce the idea of vectors. So, if the basic introduction for a vector, so say we are traveling in our car and we travel 3 miles north and then we travel 4 miles east. How far did we travel? Well, we can think this as a total distance. We could say, well, we traveled 3 plus 4, so the miles are going to change on our card to become 7. But then we can also think of this as an idea as displacement. So I could think of, well, if I connect those 2 points from my start to my finish, really that is going to give me a right triangle. And so I could find the length of that hypotenuse. And so my displacement is going to be found by taking the square root of 3 squared plus 4 squared to get 5. So my idea now, if I asked how far did I travel and you said 5 miles, well, that would be true in terms of my displacement. So this is a vector. So the idea of a vector is this piece right here, our displacement. And so to further explain, so a vector is a quantity that has size, so size is what's called magnitude, and a direction. So examples of vectors are displacement and velocity. So I talked up here that this is a displacement. And then we have another idea that's called a scalar. So a scalar is a quantity that has size but no direction. So an example of a scalar would be distance and speed. So we could think of as a scalar was my route that I went this direction. Another thing to think of with scalar, weight is also a scalar. So you could think of weight on a scale. Scalar, weight, it has a quantity, has a size, but does not have any sort of direction to go with it. So let's take a look at how we could represent vectors. So say I had some vector, I'm going to say A and B. So I have A and B. And I could say that A is at 0.23 and B is at 0.57. Okay? So to move, if I wanted to move from my point A to my point B, I could think of this, well, in order to move that, I'd use 3 units in the positive x direction, and this isn't 3 plus x, I'm just abbreviating, 3 units in the positive x direction, and 4 units in the positive y direction. Okay, so this move right here was my horizontal move, and this right here was my vertical move. So now using vector notation, we say that our vector A, B, because I'm traveling from A to B, now I'm going to put an arrow over that, saying that I start at A and I go to B. I'm going from A, B. That does not equal BA. Okay, so don't get that confused. That would be saying if I started at B and went to A is what this is. We are focused on this one, A to B. Okay, so I can also represent this in column form. So my vector AB, well, in column form, it's just X, Y. It's not a fraction. It's not a combination that we've worked with. It's just X and Y stacked vertically in a column. And then now I'm going to represent this as 3, 4. Also, another way to represent this is using variables, where I'm going to write it as 3i plus 4j. These variables, this I and j, all those are length of 1 unit. Length of 1 unit. Okay, and those are also called base vectors. Okay, another way that we can represent this AB is you'll see it written as a bold lowercase letter, so a bold lowercase a. Well, it's oftentimes hard to write bold lowercase letters unless you're typing on a computer, so you might see it written as that lowercase a with just a line under it. Okay, so that's another way to represent that that vector AB. It's just a lowercase a with a line under it. So there's multiple ways that we can represent this, and that's one of the pieces that I want to make sure we are good on to get this foundational knowledge. Okay, so that was represented two dimension. So if I went up and over, what about now if I'm in 3 dimensions? So this is represented, I could have 3 pieces. So I'm going to have my I is still going that horizontal, my J, and then also my letter K. Okay, so this is going to be in 3 dimensions. So say I have some vector that is 3, -2, 1. I can represent that by saying, well, 3I minus 2J plus K is how I'd represent that. And so again, this is moving in the positive X direction. This is in the negative Y direction. And now this is the positive Z direction. So the XY coordinates, if you think of it in 3 dimensions, that third dimension is represented by the variable Z. So here again is this kind of a recap. So the unit vector in the direction of the x-axis is I, so we know that. So in 2 dimensions it would just be 1 over 0, and in 3 dimensions it would be the column 1, 0, 0. Y is J, so 0, 1, 0, 1, 0. And in 3 dimensions of the z-axis, which is represented by variable k, 0, 0, 1. We will not have it in terms of a 2 because we cannot have a k in 2 dimensions. It's always going to be our third dimension. So the vectors I, j, and k again are our base vectors. So again, we talked a little bit about magnitude, where magnitude is representative of the length of the vector. And so now we can look at how that is denoted. So it looks like absolute value bars. So if we have absolute value bars of some vector, that is representing the magnitude, which is the length of that vector. So again, from our first one, if we have AB, so our AB, and again, can be represented with a lowercase a, the magnitude of it is the actual value of it. So the length of that would be 5. So the formula it tells us is just vector AB, represented in column form AB, which is the same as saying AI plus BJ. Then the magnitude of AB is going to be the square root of A squared plus B squared. Okay, and these are not bold, so that that lowercase a and that lowercase b are not bold. So that's just talking about here and here. So that's that lowercase a in bold isn't used very often just because it can become confusing. And then in 3 dimensions we can say, well, AB is represented by our column vector of ABC, AI, BJ, CK, and then now it's going to be the square root of A squared plus B squared plus C squared. Okay, so we have all these vectors. So when are vectors equal? When are they negative vectors? When are they parallel vectors? So we can look at each one individually. So 2 vectors are equal if they have the same direction and the same magnitude. So that's key right there. Same direction and same magnitude. So the same length and the same direction. Their I, J, and K components are equal too, and so their column vectors will be equal. So let's look at this. So if we look at this, vectors, we have A and B, and P and Q are pointing in the same direction. You can see that by the little arrow there in the center, pointing in the same direction, so they're parallel, and have the same magnitude, so the same length. And you could check that by finding out the length of each individual one. And then now 2 vectors have the same magnitude but different directions. Again, by that arrow right there in the center, where MN is going this direction, AB is going this direction, so they are not considered parallel. And then finally, if we write AB is 2, 5, MN is -2, -5, so AB is actually the negative of MN. MM is called the negative vector. So we could write AB, if we wanted to switch it around to go in the other direction, we would just say negative BA. So again, getting back to the idea of the parallel. So these 3 vectors are telling us they are parallel, but have different magnitudes, because AB is actually 1/2 the length of CD, and then AB is actually twice the length of EF. So here AB is half of CD, AB is 2 times EF. So now I can say two vectors are parallel if one is a scalar multiple of the other. So AB and RS are parallel if AB is equal to K, where K is the scalar quantity. So do not get that confused with the K of our three-dimensional vectors. So this is just K as in some constant. So it's a scalar quantity, it's some constant. And it also can be written as boldface A equals K times B, boldface B. So again, vectors A and B and G and H have the same magnitude, so they're the same length, but different directions. So they are not going, they have to be going in the exact same direction for these to be parallel to each other. So now let's look at the idea of position vectors. So position vectors are just vectors giving the position of a point relative to a fixed origin represented by the letter O. So that's the important part, the fixed origin O. So we're creating some vector from that fixed origin O. So our point P with coordinates negative 5, 12 has a position vector from O to P represented in column form, negative 5, 12, or using our I and J of negative 5i plus 12j. So formally, the point P with coordinates xy has position vector of OP, where P represents some point, of xy, which is equal to xi plus yj. Okay, another idea, resultant vectors. So looking at our diagram, consider the points of 2, 3 is our point A, and B is at 6, 6. So the diagram shows these points. We can see that the vector AB is from 4 to 3. So in order to get from A to B, I need to go over 4 and up 3. Now we can also see that to move from A to B, we could describe the move as either going directly from A to B, or first going from A to O, so going back to our origin, and then from our origin going up to B. So from here we could write it as, well, instead of just going A to B, I could go AO, or my position. I need to make sure I'm giving it in the right order, so A to O, and then from O to B. So the vector AB is called the resultant vectors of AO and AB, or AO and OB. And then recall that AO, my distance AO, is the same as the negative of O to A. I'm just changing my direction with that. So there we could say that OB subtract OA is going to be our vector AB. So formally, to find the resultant vector AB between 2 points A and B, we can subtract the position vector of A from the position vector of B. So let's do an example of this one. So points A and B have coordinates. So now they're giving us into three-dimensional coordinates. But we do not necessarily have to graph these coordinates in any sort of 3D plane. So if I just want to think of it, if I start out from some position O, and I want to go looking at A, I'm going to say negative 3, 2, 0. So if I want to figure that one, so let's draw this. For point A, let's start out with some origin O. So I have coordinates of negative 3, 2. So if I continue this over negative 3, up 2, somewhere right about there. And then if I have negative 4, so I'm going to keep going over, up 5, I'm going to be somewhere up here. So this is my B, this is my A. So find the vector AB. So I want to find this vector here, AB. Well, I know I'm starting out at O, so I can see this vector right here from O to A. And then now I want to find this vector from O to B. Apologize for these squiggly lines. So let's try and draw this again a little bit clearer. So if I have my original point here as O, and then I'm going over some distance and up to get to A. So I have that line there. and then my B was up here further, that vector there. So I'm trying to find this one right here, that A to B. So they give it as a diagram, but I wanted to show it to you from O as well to see what that looks like. So our first position vector, my O to A, on my diagram is represented by -3, 2, 0. So we could see that one pretty clearly. And then O to B is my other position vector up here. And now, using our formula, when I have AB is going to be represented by that OB subtract OA. And so I have it in column form. Well, OB was this piece right here, -475. OA is this, -320. All right, we'll talk more about this later, but this is kind of a preview. Whenever you add or subtract vectors, you just go straight across in each one. So -4 subtract a -3 is -1. 7 subtract 2 is 5. 5 subtract 0 is 5 as well. So my AB, I would write, is -1, 5, 5. Okay, so that's the end of this video. There'll be a couple questions at the end of it, and come to class with any additional questions, and we'll get started on the classwork.